Hi there everyone, welcome to the video lecture series on complex integration. I'm Mayur Gohil. This topic of complex integration is extremely crucial for the students, those who have taken up their paper as complex analysis, or if you have this topic in your syllabus by any means. This topic is useful in image processing and in further calculations of related to electrical circuits and signals. Now, for mathematical understanding and solving purpose, let us see how what all things are important for um, solving of complex integration. Let us see here. The first important thing that is required is this formula that says let z equals to x plus iy, then dz equals to dx plus I dy. This is very important. We will need it all throughout. Okay. Further, it is this important formula f of z equals to u plus iv, where u is the real part and v is the imaginary part. Okay. If your function is written in this manner, then you can have this integration formula in this way. It's very straightforward to derive this formula. Let us see it quickly. If you have I equal to integral over a curve C, okay, f of z dz in this way, you substitute the value for f of z and dz over here. So on substitution you get u plus iv, and for dz you will get dx plus I dy. Okay, now let us uh, multiply it in an ordinary way, the way we generally do. So you get u dx plus iu dy plus iv dx plus I square v dy. Now we know that now I square is minus 1. We all know this, right? So we have over here, therefore I is equal to integral u dx plus iu dy plus iv dx minus v dy. Okay. Now what we do is we collect the real part, the terms which are other than I, and we collect the terms with I. Okay. And we split up the integral. So what we do is I integral u dx minus v dy, and then I collect I over here outside. I take it, I is a constant. So now here I am left with u dy plus v dx. Okay, so this is the integral, and uh, that's the formula what it is saying. U dy plus v dx, you can swap it and write, because it's just a mathematical notion to write x first and then the y, so it's just like that. V dy plus I integral c v dx plus u dy. Okay, so this is the formula, how this formula has come into the picture. Now, what is the importance of deriving this formula and understanding? The key thing over here is to understand that we must separate our function into the real and imaginary part. The solving of the integral becomes easy if we uh, collect the real terms together and the imaginary terms together. That is what this formula is basically talking about. There is more to it. You can see something similar to Green's theorem over here, etc. But I'll not deal it over here right now. What is important over here is that we need to understand that collect the real part together and the imaginary part together and then solve. That's the key thing right now. Okay, now let us go for the further thing. In Cartesian coordinate, the equation of the circle is given in this manner: x minus alpha the whole square plus y minus beta the whole square equals to r square, where I hope you remember that alpha and beta are going to be the center of the circle. Okay, I'll just mention over here. Let me take up, yeah, where center is alpha comma beta and r is the radius. Then in complex plane, the equation of the same circle is going to get converted to modulus of z minus alpha plus I beta equals to r. Let me give you a small example regarding the same. Okay, so let me take up an example. Let's say we have a circle whose equation is x minus 2 the whole square plus y minus 1 the whole square equals to, let's say, 9. This is the equation of the circle. Then in complex plane, just compare it with what we have seen here in the theory. Then in complex plane, this equation of the circle will be mod of z minus alpha is 2, okay, then plus I times 1, okay, that's going to be 1 itself, and I times 1 is I over here, and then you have radius, which is the square root of this number. So square root of 9 is always positive, we are supposed to take for radius, so that's going to be 3. So your equation of the circle is this. Now if we take another example, let's say x square plus y square equals to, say, 4. Then you have over here, it will be, since here you don't see any number instead of alpha and beta, it means alpha and beta are 0. Okay, so origin is the center over here, so this will be z, basically it will be z minus 0 comma 0, 0 plus 0 I, so that is mod z over here, and you have radius equal to 2. So mod z equal to 2 is the equation of the circle in the complex plane. Having settled down with this explanation, let me take up a small example on complex integration and how to solve any question related to complex integration. Let us take up this small and easy example. It says evaluate the integral 0 to 1 plus I z square minus z dz along the straight line y equals to x. Now, in order to solve this integral, there are steps that we need to follow. We cannot haphazardly start over here. So first thing, you have to focus upon the limits over here. So let me write down the step here. It says, yeah, I'll write with this red. Step number 1, we'll understand limits, take care of the limits. Step number 1 is that from limits you understand what are the points. Okay, so step number 1 we got for limits, understand the limits, given limits. So let us see what do they mean. So the lower limit over here is, let's say I call it as a point A, which is a complex number 0. Okay, so this is basically 0 plus 0 I, and I can write this now as 0 comma 0. Okay, so they basically it's a origin a 0 comma 0. Now we have the line, another point is there, b 1 plus I. So this here you have its x coordinate is 1 and the y coordinate, the coefficient with I is 1 again. So here it's 1. So I have got 2 points a b which is 1 comma 1. Sorry, a is 0 comma 0 and b is 1 comma 1. Now it is very evident over here the equation of AB is y equal to x, because this is the line which is, if we draw a diagram over here, let's say I draw this diagram, then at this I have my 0 comma 0, and if 1 is here and then there is 1 here, then at this point we have this line y equal to x, and this is the point which is b. Okay, so that's what the line is over here, x to y. Now from, and they have already told us the straight line is y equals to x, and also these limits which are given to us, they are in line, they are aligning with what is told, so we need not worry now. Let us see. So from the limits we are able to get the points which are there, and we have also got the equation y equal to x. Now step number 2 is, let's see, step 2, we need to find dz. Okay, step 2 is to find dz, to find dz. So let us see how to go about it. So let z equal to x plus iy. Okay, let z equals to x plus iy. But now here one thing we now know, that we mentioned that dz equals to dx plus I dy. Alright. Now call this formula in step number 1 what we derived as our first part. Okay. From 1 we can see that from 1 dy is equals to dx. Right? Therefore we have dz equals to dx plus I dx. Now we have something new regarding dz, that is, it is, if I take dz common, sorry, dx common, I get 1 plus I dx. This is very important now. So we get another new thing regarding dz, that it is now changed from dx plus I dy to 1 plus I dx. So this is another important thing. This is step 2. Okay. Now let us see what happens in step number 3. Step number 3 is to simplify the function. Step 3 is to simplify f of z. So let us see how to do that. We have f of z equals to z square minus z. Okay. Now how to handle this? We already know that z is equals to x plus iy. So you substitute here x plus iy the whole square minus here you will have x plus iy. Moreover, we also know from 1, okay, that from 1 we have x plus iy now will become x plus, here f of z equals to x plus ix square minus x plus ix. Okay, that is what is the meaning. Further, I can separate up this a bit, and I can write here x taken common x square, and I'll write this as 1 plus I square minus x taken common 1 plus I. Okay, that's what I can write. Now we can simplify this expression a bit more and write it as let us simplify this more, and we write here x square, and this 1 plus I the whole square is nothing but 1 plus 2I minus, or if you want to write I square over here, it's okay. Then here it is x into 1 plus I. So this gives us x square times 1 plus 2I minus 1 minus x into 1 plus I. So on simplification, I get x square into 2I minus x into 1 plus I. Alright, so this is what we get. Now comes our, you can simplify it further if you want to collect the real part and imaginary part as the formula was suggesting. Let's do that. So I'll collect the real part and the imaginary part over here. So x square into 2I minus x minus I times x. Okay, so I'll get minus of x over here, and then I'll keep I common, so 2x square minus of x. This is the imaginary part over here. So that's what the function f of z, when we wrote it over there u plus iv, that's what it meant. Okay, this was your function f of z, and that's what u plus iv meant over here, real part and the imaginary part. Now we go for the integration. Step number 4 is for integration. This is optional, okay? Writing u plus iv is optional. You could even do over here. At this point also you could have integrated, but I have just done it in line with the theory. Step number 4 is to solve the integral. So let us see how to solve this. We had I equal to integral 0 to 1 plus I z square minus z dz. Therefore, now when I substitute the function over here, I see it is minus of x plus I times 2x square minus x. Okay, and this dz, the dz term is now 1 plus I times dx from 2. Okay, so I'll write here 1 plus I dx. That's how I get there. And the limits are very important now. See the limits, how do we come to know regarding the limits? The variable is x. So you observe the coordinates of x in the points that we have found in step number 1. So x coordinate is going from 0 to 1, right? Here this is the x coordinate and this is the x coordinate for ending. It is going from a to b, origin to 1 plus I. So you start from origin, x coordinate is 0, and here on 1 plus I the x coordinate is 1. So your limits are going to be x equal to 0 up to x equal to 1. Now you integrate this. So on integration we'll get minus of x integration is x square over 2. Okay, so this is 0 to 1 plus I times 2x cubed by 3, and then there is minus of x, so x square by 2, 0 to 1, and this whole chunk is multiplied by 1 plus I. 1 plus I is a constant number, so you can, constant complex number, so you can pull it outside or you can keep it aside. Now remember this integral which I am doing manually over here, you can straightforward do it in your calculator if you are allowed to use calculator at your institution or in your examination. Okay, so right now I'm doing it without the calculator, so I get the answer over here, I equal to minus 1 by 2, and when you substitute 0 it's gone, so plus I times 2 over 3 minus 1 over 2. Okay, so that's what you will get, and it is multiplied by 1 plus I. So on simplification, minus 1 by 2 plus I times, here you will get 4 minus 3 over 6, right? And here it is 1 plus I. So when you do the multiplication here, you'll get minus 1 by 2 plus I times 1 over 6 times, here it is 1 plus I. I'll just put a line. Okay, yeah, so that's the answer there. And then when you multiply this with minus 1 by 2 plus I by 6, you will get the answer over here. On multiplication you must get I equal to you will get minus 2 by 3 minus I by 3. This will be your final answer. Okay, so this is how you calculate the complex integration. So there are four steps. First is finding the limits. Second step is finding dz, appropriate dz. Third step is simplifying f of z. Fourth step is solving the integral. Remember, here while solving the integral, I have done here manually. You can do it once you find the correct real part and the imaginary part. You can straightforward calculate each of the integral individually in your calculator, and finally you multiply and keep. You can delete these calculation steps. You can let calculator do that, and you can write your final answer. Because if calculator is allowed in your examination, then that's what calculator is supposed to do. It will help you to calculate it. So yeah, so this is the basic example on complex integration. I hope you liked it. Please like the video and share it with your friends, who those who need it. Okay, till then, keep solving good amount of mathematics. I'll sign off. Thank you.